Alright, so this is the fifth video in the Yocto Linux series. I want to do a couple of things in this video. The first one is we need to get the 7-segment display from our Vivado project and get that bit image, the bit stream that is used to configure the FPGA, onto the SD card so that we can actually have the hardware that we developed in Vivado available to us through Linux. And it turns out that there's a couple of different ways to do this. If you want to have the file be able to be loaded from the SD card when you first turn the machine on, which is kind of what we want to do, we have to be able to get the bit stream over and turned into a bin file. And I found this reference on the internet from 2015 in December. There's a Python program, and I've actually seen a number of references to it. This Python program will read the bit file and turn it into the appropriate bin file. It's part of another Yocto Linux project. We don't really need the whole thing, but what I'm going to do is I'm going to go ahead and clone it. So I'm just going to go to, this is a standard GitHub page. There's a link here for clone. I'm going to clone, copy that link. I'm going to go to my Pokey directory and do git clone and hit paste. And it'll download all the project files into there. And if I do a quick search here with find, I can look for the FPGA bit to bin. And there's that little Python program. Now, the next thing I need to do is I need to get the bitmap file. And now the project that we were using was through Vivado under Windows. And what I've done, is I have created a shared folder through VMware. So I can go here to VM and go to Settings and go to Options and turn on Shared Folders. And I've turned on 2 shared folders, my Windows Home directory and my Vivado directory. In some versions of Linux, these were always available kind of automatically. It looks like in Ubuntu 16.04 that's not the case. And so what they do give you, though, is this program called VM HDFS. This is the host guest file system. And Fuse is a user-mounted or user space file system. So this doesn't need any support from the Linux kernel to operate. And when I hit enter here, it's going to mount that directory, mount HDFS, and bingo, there are the folders that are in my host operating system. And so if I go here now, I can copy from Vivado, CMP 420, go to my 7 system. The bit files are going to be in the runs directory and in the implementation directory. We'll just do a find command for them and find them. Oh, not there. Okay, we can do a find for them. In case you've not used the Unix find command, it's the find command, the directory you want to start your find, and then you do -name, and then in the double quotes here you can put a wildcard. And so I'm looking for that bit file, and I want to copy that bit file to here. And since there's really only the one, I can use the cp command, and this is a really cool Unix trick. The backtick right above the tab key on my keyboard can be used to take the output of one command and turn it into command line arguments for another command. And so in this case, the find is going to give me a list of file names, and I'm going to be able to cp those files to right here. And sure enough, there's my design1 wrapper.bit. So according to that website, if I do a Python FPGA and I do the flip and we do design1.bit and we'll call it fpga.bin. At this point, it's created this fpga.bin file for us, and it's just a little bit. It looks like it's actually a little bit smaller than the bit file. I'm not exactly sure the difference between these two file formats, but I do know that what I need to do next is copy that into the SD card interface. So I'm going to make sure that I have that SD card mounted. That should be there. Oh, it's in media. So there's the root file system, the boot file system for my SD card. We'll copy the FPGA bin file to it, and we'll eject dev SDD. The next thing I'm going to do is take the disk out, put it in my Z board, and hit the reset button. And after a few seconds here, we should see the Z board reset. Maybe. There it goes. And most importantly, it just scrolled off my screen. Let's see if I can scroll back here. We see that it is kind of like right in here. It's loaded up the fpga.bin file. You'll know that it worked because the blue program light come on to indicate that the programmable logic part of the system has been programmed. And so we're back in business. I now have a Linux system that can access the 7-segment display because it's been put into the AXI bus and it's been given a memory address. Before we start the next step, I just want to review the hardware configuration that we're using here. The 7-segment display was located at memory address 43C00000, and that was done by Vivado when I made the system image. We could have put this thing anywhere. It's reconfigurable hardware after all. But that's where it is right now, and what I've done is I've kind of written up some documentation to go along with the controller. You might remember from the previous 7-segment videos that we had a control register, and the upper 14 bits or 15 bits were connected to the anodes and cathode drivers directly, and then down here in the lower range we had the 12 or 24 and then the mode. And what I've done is I've just actually kind of stolen Microchip's documentation format for the PIC32. They say that plagiarism is the highest form of flattery, I guess. But it's a nice, clear, and consistent format for documenting what bits are where. Good job, Microchip. The other register is the seg value register, and it actually has two interpretations. When the mode is for the 7-segment display is a 1-0, mode 2, it's going to be displaying the 7-segment digits, the BCD digits, and if it's mode 3, it's in time mode and it'll operate as a clock. The set time is the time period register, and then we also have the colon period register, and those are just two 32-bit counters, and they're only used during during mode 3. So we can use this now to access our device and kind of make sure that things work the way we hope that they're going to work. Alright, so the next step is to be able to connect to the IP, the 7-segment controller that's in the programmable logic from the ARM system. And I've already started. I have a sample program here, and I'm just going to walk through the different parts of this. The include files here are the standard include files you'd expect to see, the standard IO, standard lib, and whatnot. But then I have I have a variable here for the segment address. This is the base address of the 7-segment controller that was assigned by Vivado. And so for our particular instance, that was in hexadecimal 43C00000. So that's a regular 32-bit address. But it's a physical address. And so to be able to access that peripheral from the Linux system, which is on the virtual memory, I'll need a way to kind of map that physical address into my process space. Okay, I want to just take a moment and talk about how physical and virtual memory are implemented in these systems. You know, the idea here is you have your physical memory, and we conventionally just kind of draw this as kind of a box, and down here is byte number 0, and up here is whatever your memory size is minus 1. And if you have say a half a gig system, you have 0 up through 512 megabytes up here. Part of the goal of any operating system is going to be to have a virtual memory space today. And in the virtual memory space, basically what we can do is we can have processes, and let's say I have process ID number 101 over here, and it's going to have a virtual memory. And as it grows and shrinks, it's going to allocate memory through the operating system. And in this way, let's say that the process tries to access memory here that doesn't exist. You know, it's going to end up crashing the system. And so part of the job of the memory management unit is to protect the process from interfering with memory and using memory in a way that doesn't exist. And in fact, if you've done any C programming, I'm sure at some point you've seen a seg fault. Anytime you do a seg fault, it's because you've gone outside of the virtual space that's been allocated to your system. Although mentally we picture this as contiguous range of memory, there's nothing that says that this has to be contiguous. There could very easily be, let's draw a little break in here, and even a break in here. You know, oops, go back, get my pen back. So for example, this could be your stack, this could be your heap, and then this could be your text segment. And these things could be scattered all over memory. There's no reason that they have to be contiguous. In order to pull this off, remember, if you've had a computer organization class, I'm sure you've seen the memory management unit. And the memory management unit takes in a load or a store from a program dynamically, because remember, the operating system can't do it. While a program is running on a CPU, the operating system can't be. So the MMU is a piece of hardware that actually interjects between the memory and the processor, and it's going to translate that virtual address into some physical address and direct that load and store to the appropriate place in memory. And to do that, the MMU maintains, maintains a table called the TLB, the Translation Look-Aside Buffer. And inside here is going to be the process number and a page number and then a physical page number. And for efficiency, we don't map individual words. Instead, what we're going to do is we're going to break down memory into pages, all the same size. And for example, 4K pages are pretty common. And so if I have 4K pages, I need 12 bits is 4K. That's 2 times 2 to the 10th 4K, or 12 bits. And so let's say that I have a 32-bit address space. That means I need the bottom 12 bits are all on the same page. That page is only now 20 bits. So a page number out here is 20 bits, and over here page number is going to be 20 bits, and we'll have some number of bits allocated for a process ID, let's say 16 bits. And what this allows me to do is really efficiently store this in hardware. I don't need to store all 32 bits over here. I can just kind of organize things as pages. So for example, over here we might have process ID 101, its page number up here. Let's say that this page number is F0000. That's remember, each one of these is 4 bits, so there's 1, 2, 3, 4, 20 bits. So F0000, that's the stack. And let's assign that to page number 21000. So essentially what we've done is we're going to connect the stack to, say, that page there. Maybe the heap will have some pages that go this way, and the text segment will go in this way. And maybe later on we'll even allocate, oops, I keep making the brush bigger. Maybe we'll even allocate even more to the heap, which means we'll need to allocate another page onto the heap. And so that's basically how virtual memory works. And of course I can have another process and it's going to have all of its pages and so on and so forth. But why does this matter for hardware? In most computer systems you actually have a physical memory that is actually making full use of the address space that the processor can use. If I have a 32-bit address space, that's 4 gigabytes of space. In a system like the Z board, we might have, and this isn't exactly the Z board's arrangement, but we might have the 512 megabytes of RAM allocated to a range of addresses. So maybe 1000 all the way up to whatever the end of that would be. I know that's not right. But we might also have the flash storage loaded into memory someplace else. And there's really no rhyme or reason that it has to be one way or the other. It's just that that's how the system architects designed the system. In our 7-segment display, we know that we have a peripheral sitting here at 43C00000, and it's going to go up to 64K, so 43CFFFF. Oops, sorry, that would still be 0. And there may be other peripherals up here, so like the GPIO or the Ethernet. These are all used by the ARM core, and they're way up in memory. They're in the 8,000 ranges. And this is still physical memory. So because of the virtual memory system here, if I get a virtual pointer, even if I say I want that virtual pointer to be the 43C00, that's where the 7-segment display is, it is almost certainly not going to point to the appropriate place in memory. So instead, what I need to do is I need a mechanism to ask for a mapping to be created in the MMU. And so essentially what I need is, in the MMU's TLB, I need my PID number and my page number to map to the physical address. And the only thing that I really know is I want that physical address to be the 43C000. But remember, the bottom 20 bits of that, or 12 bits of that, are all gone. So, and they're gone because that's a page. So I want that page number, and I want to map it into my process page number. And I don't care what that process page number is. I just know that if I have that map, then if I do a load word from, let's say I have my well, load immediate. How about that? Load immediate of 320000000. If I were to load that into S0 and load 0 bytes away from S0, that's going to load. That's going to load from memory address 3200000, and when it does, the MMU is going to rewrite it and direct it to the appropriate peripheral. So I need that mapping to be created so that the MMU can be fooled. Instead of reading from RAM, it can be fooled into reading from my device. And in Linux, we're going to be able to do that in the user space by using the special device driver DevMem. And then we're going to go back to the video here, and you're going to see how we use that DevMem to fool the MMU into creating that map into a physical space. To do that, I'm going to use the DevMem device driver that's built into Linux. DevMem serves exactly this purpose and is a workhorse for embedded systems development. By opening this device, this is a character special device, kind of like where we're going to be building soon. I'm able to do a number of different kinds of system calls. Most importantly is this next one, the mmap system call down here. But for now, I'm just going to open it like I would open any other file. And in fact, this is how you open up all the low-level devices in Linux. So if you have the permission to access this device, then you are able to use this device. I mean, that's kind of the way it goes. The next pair of system calls, or the next system call here, is the mmap system call, or memory map. And the way this works, there's a number of arguments to this function, or this system call. The first one is if I want a virtual memory address to be created. I don't care. Pick one at random. The next one is the size, and I was experimenting with different sizes. The skip page size is the default page size of your memory system, often 4 kilobytes, whereas this up here would be corresponding to the 64 kilobytes that was reserved for the peripheral by Vivado. Either one is fine. I meant to change it and didn't. The next thing is whether we want to be able to read or write, and I want to do both. How do we want to map this page of memory? I want to map it so that I can share it or private, either one. This would allow me to have multiple programs running on it. The file ID that I've opened, so in this case I want to map part of DevMem into my memory space. And what offset do I want to use? Well, I want to go this number of bytes away from the beginning of memory. And so by giving it that offset, mmap is going to map the physical space into a virtual address. This base pointer is going to be somewhere in memory. I don't know or care where, but it's going to be assigned to this map process's memory space. The way to check to see if mmap failed is to compare the pointer that you get back to the variable mmap failed. It should be the equivalent of a -1, and if it is, we'll exit. The next thing I do is I print out, remember in C language a pointer has duality with an array, so that an array and a pointer are the exact same thing. So by allocating a pointer to an array or a pointer to uint32t, I also get to treat it like an array. And so this little thing here just prints the value of the 4 registers that we looked at over on the register overview. The next part of the program, I just print out a little prompt and get some input. And then I use the str to long function to be able to convert or read from the string and convert the values that you type in to a register number and a value. And if you enter a valid value, I will write the value to memory. And so, for example, once I have the C file written, I want to compile it. I don't have a C compiler over on the Z board, and so I'll use a cross compiler here on my Linux machine. And so I've installed the ARM Linux cross compiler, and I'll compile map.c to the map executable. Because this cross compiler doesn't have all of the information that the Yocto Linux cross compiler does, I was having some problems getting the libraries to match between the 2 versions. And so what I've added is the static option, which creates a static executable, a program that does not need any link libraries. And once I've done that, now the map program can execute over on the Z board without needing to have the same set of C libraries that I have over on my PC. The next thing I do is I copy it to that TFTP directory. This is the same TFTP directory that I made in the previous video. Now I'll take a look at the other side here. We can bring that file over with the tftp command. So this is the same kind of tftp command that we used in the previous video, only this time I want to transfer the map file, and then we'll run the map command. And what I see is that the map command has, I've already set it for mode 3, which is the timekeeping mode. It looks like we are set for 4:31 and 29 seconds, which is about the right time. Yep, it's the right time. And then I know that I've set the timeouts for 100 mega count. But we could change that. Let's change the timeout count for the colon. And that would put the colon on a faster blink rate if I had that option turned on. I don't have it turned on right now. But what this demonstrates, and in fact we can even see that the clock is running, and it is got the current time and date. So that's user mode access to a device. One of the comments we can make about this is, if you are the developer of this program, you have got to know everything there is to know about the device in your C program, and your C program is responsible for controlling everything. And so this makes it really, really hard for people to be able to share their devices and their device drivers, because every application's developer would have to know everything about every device. We don't really want to do that. So the role of our device driver that we're going to build is to make access to the 7-segment display's features easier for the average Joe Schmo programmer. And in fact, if I do it right, we can even access it right from the command line. So it's time to go ahead and get started with the actual kernel module. What I've done is I've changed my directory into the Pokey Meta 7seg directory. This is the layer that we created yesterday to do the Hello World module. And in fact, here's the top directory for that Hello World module. What I can do is use the Unix command cp to copy that entire directory, and I'm going to make a new directory, and we'll call it 7mod. And what I want to do is just kind of walk through these files, and anytime I see hello, I want to change it to become 7. So we're going to rename hello mod using the move command, or mv command, to be 7mod, and we'll give it a version. And I'll edit this file and look for hello anywhere in here. There it is. So we'll change that to be 7.c. And then in the 7mod files, I'll move hello to 7.c, and in the make file, I'll change that to be 7.0, and that's the last of it. So this is basically doing the exact same thing our hello module did in the previous video, only now it's called 7mod. To make this thing a little bit more useful, we want to be able to go through here and actually have it do what it's supposed to do. Alright, so instead of going through the process of developing a kernel module from scratch, kind of we'd be here for a while, I wanted to maybe just show a mostly completed driver program, and then allow you, the user, to kind of follow along. And what we'll do is maybe we'll go through here and annotate the different parts of the program, and then we'll talk about what's happening and why. At the top of the file we have our normal includes, except that in this case they're normal includes for Linux kernel code, and so instead of being able to use the familiar standard.io and unis.h and all of those normal .h files, this module is going to become part of the kernel, and so of course it has to have the kernel specific versions of those. Just as we did in the Hello World module, I want to keep track of whether or not the device is already open. I don't want to have two users using this module simultaneously. We also have some buffers here. And probably we should go ahead and make all of those static. The reason why they're static is these are not able to be seen outside of this C file. Anytime you have the static modifier, it's almost like we're having a local variable. It still is stored globally in memory, but it's not visible as a symbol outside of here, and so it kind of gives it just a little bit extra protection. So these next two lines are pound defines for defining the character driver nature. So we're basically saying that this guy is going to live on major num 202. He's going to have a character device name of 7. This is our 7-segment display, so that makes sense. This is, the base address of the 7-segment display. I'm going to put it to do here. When we load a module, oh, nope, that's not what I wanted to do. There we go. Just take that last guy out. When we load a module, Linux allows us to specify a command line argument. And since this is reconfigurable hardware, this module could be anywhere. And so it'd be really nice to be able to change the base address without having to recompile the kernel module. And so to do that, we can pass module arguments on the command line when we insmod or mod probe the module. But for now, that's what it is. Here's our ioctls. In the previous video, when we did an ioctl, that was one for setting the mode one way and one for setting the mode the other way. Remember, we did upper and lower case for the Hello World module. This is a little bit different. If you notice, I'm using the IOW instead of just IO. This is an ioctl that you write, and we're going to call it what's going to be on major number 202, and it's number 0, and you're going to write an integer, so you're going to send me 4 bytes. And we'll see later on when we use this, that would be an ioctl that we would want to send an integer to set the mode. I should put another to do here. This needs so this ioctl needs to be kept consistent with the user space code. If I don't, then what's going to end up happening is the ioctls won't match, and then the user program will fail. This here is a base pointer. In a previous video, I had done the mmap system call for mapping a device into memory. This is basically doing the same thing. Even though Linux, the kernel, has access to the physical memory, Linux, the kernel, also uses virtual memory to protect its internal structures. What that means is I can't just go writing all over physical memory. I have to map it in just like I did before. And so this pointer is going to be the pointer that I get when I remap that physical memory. Notice it also has this annotation, this __ iomem. This is a pound defined that's going to be used by Linux kernel to kind of make sure that this memory pointer has some extra properties associated with it during compilation. This is the module that allows me to handle a read, and what happens whenever we handle a read is I have to essentially be able to respond to a user who's going to read, and I want to be able to handle line at a time kind of output. What's going to end up happening is whenever I don't have a message, or when I've consumed all of the bytes of the previous message, I'm going to reset the message. And so what we see here is we see a detection. First of all, if the offset is equal to null, then there's a problem there, throw an error. But if the value that offset points at is 0, or the number of bytes in my message is equal to 0, that tells me that I've hit the end of my buffer, and I'm going to recreate that message out. Remember, message out was one of the strings defined up here at the top of the file. So there's message out and there's lang out. And what's going to happen here is while essentially we're going to get the mode. So we're going to read from the base address of the 7-segment display, get the mode. And if I'm in mode 0, I'm just going to sprintf a message out of whatever the current mode is and tell you that we're off. If we're going to, if we're in mode 1, I'm going to get the anodes and cathodes out of that base address register, and I'm going to print them out with the mode and then cathodes and anodes. And the same thing if we're in BCD mode, I'll tell you the BCD value, and then if we're in time mode, I'm going to format the time to be hours, minutes, and seconds, and then I'm also going to tell you what the period register is. Once I've sprintf this into that message out buffer, we're going to store lang out to be equal to the message out length as a string. Remember, that's what sprintf does. And then the while routine is whenever we're reading, we're just going to keep on reading until we either fill the output buffer, that would be the out B buffer that the user is requested to read, or we get to the end of the message. And when we get to the end of the message, we're going to reset the number of bytes that are available. So let me show you how that works. I have this module loaded onto my Z-board system, and if I cat from dev7, right now I'm in mode 3, and my timer, my time is 11:33:39. Remember, those are BCD values, and so that's why, let me scroll this over just a little bit. So when I do that sprintf, we can see here there's my mode equals 3, time is in BCD, and my period is 100 million. So it's kind of neat. You can kind of get an idea of, a little bit better idea of how these things connect when we can see that we can read from a device driver, and we see how that value is coming out. Oh, if I do it again, whoops. I can do it again, and we'll be able to see that once I got to the end of the message, it got reset. Handling writes are a little bit more difficult, and when we handle the writes, what's going on here is that I have to be able to write values to the device until I get to whatever the end of the message is. In this case, I'm doing a line-oriented device. So when you get to the end of the line, you have to essentially handle the previous line. And so that makes this code a little harder. And what's happening is you might be writing 1 byte. You could be writing a byte at a time. You could send me a whole line at a time. If you're writing to my module, you could even send me a block of data, 1 huge block at a time. And what I've got to do in this code is I have to kind of pick up wherever we left off from the last write and begin writing the new data. And then what I'm doing is I'm looking for that new line. If in the middle of writing, and the way that we're going to handle writes is we're going to kind of read character by character from the input string. Notice here we're using this get user, just like we used put user to print out before. Now we're doing get user to read values from user space. If I get to a line or a character that's the new line, that tells me I've got to deal with it. And what I'm going to do is I'm going to chomp off that new line character, turn it into a null, and then I'm going to process that string just like I would in any other C program. So we're going to, in this case, I'm going to read the mode from the base address register, but then I'm going to turn that string into an integer value. So whatever value you've typed in. if I did this, when we did this in the mapper program, we used str to L, but that doesn't quite work in the kernel. So now we're going to have to do an str, or a simple underscore str to L. This is a kernel version of that C function. And then based on that value, I'm able to, or based on the mode, I can then handle that value however it's appropriate. So for instance, if we're in mode 1, I'll take the value that you've sent, shift it over 17 bits, and store that into memory. For instance, here's writing to the time register, and we're going to take the bottom 12 bits. 12 bits? No. Yeah. 20 bits. And then we're going to store those in that first period register, or the value register on our device. And we're going to do that with write L. Write L is the kernel way of writing to that memory. Other than, and then once we get to the end, we're just going to reset where we were. So len in goes back to 0. Otherwise, we're just going to keep incrementing len in until we either get to the end of message in other words, it's full, and then we throw an error, or we get to the end of input. And so the way this works is I can use, this is from the command line, I can actually just echo and I see that from coming from the kernel, I actually see the message from dmessage. So for instance, if I do the dmessage command, we see that it's changing time, and if I read from dev7 again, I see now that the time is 1, 2, 3, well, I must have typoed something. Oh, it overflowed in 5 seconds. That makes sense. And I don't know if you can see it on the camera, but the time is certainly 12:35. So reads and writes are working correctly. Our open code actually is the exact same thing. Oh, I forgot to change the hello to 7 there. This is the ioctl. This is essentially the same ioctl that we saw before in the ioctl test program. The close is essentially the close, and start is basically start. Here's the only difference. This is the kernel, kind of like the kernel version of mmap. In this case, I get to IO remap. So what I'm asking the kernel to do is to map that physical base address that's in IO memory into the virtual memory space and give me a virtual pointer to it. And that's what base refers to. So while the actual integer base number, this number, the #define, while that number refers to its physical place in memory, this value refers to its virtual address. And with all of that, that's it. That's the whole device driver. This is kind of a crash course into Linux device drivers, but that's it. There's no more, no less. What we've been able to do now is essentially wrap this structure around our reconfigurable hardware, and we can begin to do all kinds of really interesting things. There's lots of to-dos in this code, things to fix. As a professor of computing, I would argue that this code right here, this, what you do in the middle of this while loop, is really terrible. I would say probably it would fail code review, just because we shouldn't actually be mixing processing the string with reading or writing the string. So we'll put a to-do here, refactor into a function. So that should be a function call somewhere else, just to kind of clean that code up. So really there's lots of places we can improve things. As another to-do, I would say here at the top, using static variables is bad. Well, let me rephrase that. Using any kind of out-of-scope variables like these are kind of global scope, even though they're still marked as static. You know, we could also, just because these values, these variables are never read outside of the driver or read-write functions, move them down there. They can be static inside that variable and still have the same permanence that they have here. Kind of that scope and lifetime argument. So, I mean, there's some places to improve, but for the most part, you know, it's all in good shape. To build this module, I'm in my Pokey build directory. We do our bitbake 7 mod, just to kind of build this one module. And if there's no errors, we'll see that everything finished. I'll copy it into my TFTP directory, and I kind of got into a rhythm there when I was debugging. I would switch back and forth between that command, and then if I go up in my history here a little bit, I have a command to remove the 7 module, TFTP the 7 module, and then insmod the new 7 module, and then we can cat the thing, or echo out to it or test it. So that's it.